Hi guys, today I want to continue as requested with the interview questions. This is hardware engineering magnetics, and the first part is inductors know-how. The difficulty is very hard. As you can see, they asking you to calculate the H of L here, the saturation current here. They are asking here you to how much experience do you have with the inductors in reading the datasheet of inductor, to describe the plot of the hysteresis curve, what kind of material are you studying, and of course to plot an LTSpice. This is very infamous. I have to say, this came as a surprise for me because it's very hard that in an interview they ask you to do this. They probably want to know how much handling you have to simulate mathematical inductors on LTSpice. And then here there are a lot of questions that you have to either say correct or wrong. But again, this is a nightmare level. If you just read one of them, you realize that they are not easy. The magnetic properties of ion powered make it a good choice for many inductor applications. Ferrite materials have higher resistivity than powered iron materials, which permits them to operate more efficiently. And also, this part here. Iron-powered magnetic core typically have higher core losses than ferrites. The leakage inductance LS of the transformer is frequency dependent, and it has different LS frequency criteria if least wire is used. So this level is nightmare. Okay, they start easy if you know the formula, but then the level spikes to nightmare. So this interview is nightmare level, and they even continue with transformers know-how. So they really wanna know how much magnetic design you have done in your electronic career. And this is quite hard, so let's view them together. Okay, what is the approximately H of L value of this? We need to use paint because I want you to explain the formulas. Let's start from the beginning. So the definition of H of L is an important parameters, very, very important parameters that many designers know. Okay, so you have to know it. It is the inductance over n square. It tells you how many microhenry you have at each turn in your transformer. So this is fundamental. Okay, but you have to recover. You have to study L first. So how do you do that? Simply use B equal to mu0 times H. H is the magnetic force, MMF, and this is the magnetic flux density. Okay, and H as a definition is N times I over the gap, all the efficiency path. Let's call this gap D. Okay. Now, by definition, the inductance by definition is the number of turns over I, the current flow into it, times the flux. The flux itself is equal to the density flux B times A. Oh, well, of course, because B is the flux density. If you multiply a density times the area, you obtain the flux itself. And so this is equal to N over I times A times mu0 N I over D, which is then equal to N squared times mu0 times H over D. Now, coming back to this definition here, you substitute L to the equation there, and H of L will be equal to mu0 times A over D. Well, of course, n squared does not compare in the equation because naturally it is given in the unity measure. Is microhenry over the turns. Okay. Then let's use the calc, something Octave, MATLAB, whatever you want. that you want. So mu0, we need mu0, we need h, and we need d. So let's use this data. A is 1 centimeter square, so 1 times 10 to minus 4. And d, the gap, is 0.5 times 10 to minus 3. Ah, come on. And mu0 is magnetic field constant 1.25 microhenry. 1.5 times 10 to minus 6. So let's use this equation here. H of L, which is equal to mu0 times H over D. And the answer is too many zeros. Let's multiply times 10 to the 6. And let's see if we can obtain the first or the second. So let's multiply by 10 times 6. Okay, 0.25 microhenry. 0.5 microhenry. Okay, so this is the first correct. Going to the second, assume a saturation magnetic field of tot. What will be the maximum allowed current? Yes, this is also an important question because when you design a transformer and you design the gap, one important aspect is the saturation, okay? And you have to relate the saturation field with how much current you can get. This is very important. So they are gonna ask you this, but if you followed carefully, you know that the answer is already given. Because in this formula here, as you can see, there is already the answer. So B sat is equal to mu0 times n times E saturation over D. And so E saturation is equal to B saturation times D over mu0 times n. So even you can put n equal to 10, P sat equal to 0.37, and then we can use E sat to calculate how much current we can have. This times mu0 over, sorry, wrong. This times D over mu0 times n. 15 amps. Since I didn't use any conversion, it is 50 amps. So answer 4 should be correct. Let me say in the comment if I did something wrong, but from what I say, nothing should be wrong here. Then we go on. Describe the plot and the table explaining each point. Okay, so let me take the screen. And let's comment this on Paint. Okay, so the first graph, this is the value of the inductance. Okay, in probably this microhenry. It is a power inductor. And this is the maximum value that you can achieve when there is low current. This is a typical graph of our inductors because when they reach a higher value of current, so this will be probably a current A in amps. So this is the load current, if you want to write something. Once they reach a lot of limit, they lose more or less 20 to 30% of their inductor value. And as you can see, it matches the description. Then this graph here is probably how the inductor changes in the frequency, because the impedance of the inductor after the model of the inductor has also a resistor here, an ESR, an L, and also a capacitor C, a parasitic capacitor CP. And these parasitics here will basically influence the behavior at very, very high frequency. This capacitor in particular. the baud plot for the impedance of an inductor in the frequency is something like this. And this point here is the self-resonance frequency. And mainly because it is given by this capacitor CP taking action. It is at a very high frequency, like 100 megahertz. Okay. So this value here is probably the self-resonant frequency. But anyway, this should be also the frequency, as after a high frequency, it will start to lose value. And this is the inductance. Okay. Then, by the way, this is gonna probably a QUqestion. Then we will open on the web some QUqestion. Then they ask us which can be this parameter. Okay, since there are a lot of part numbers, watch the part number. This is my suggestion. Here there is 61, 31, 51, 102, 103. You have to know that engineers do compile the part number not randomly. Sometimes the part number contain information about the values. This happens with both capacitors and also inductors. So the main values are always stored in the part number most of the time. So this 61 can probably relate to the inductor value. So the first here will be probably the inductor value L in microhenry. And this is the main value, and most of the time they will put first. Okay. Then this value here, it's probably gonna be the self-resonance frequency, as I said before. So this is the self-resonance frequency, and in the range of megahertz. Then I think that at a very high current this can be a very high current, yes. So this is the saturation current I sat. Probably something like that. So these are power inductors, and I expect them to have, of course, a very high current capability. The number 5 should be the temperature rise. Okay, so the temperature rise coefficient, how much your inductor parameters change based on the current rise. The ERMS effectiveness of your current, how does it change when the temperature rises? This is also important for power inductors, because when they are active and the current is flowing to them, they will hit up to even 50 degrees, 17 degrees, even higher. So this table here tells you how changes with temperature. And so the only thing left, the only parameters left are the DCR, the series resistor, and it's probably one of them. I don't understand why this okay, this is probably the DCR typical. Okay, yes, this is the DCR typical, and this is DCR maximum. Yes, now I think that everything is in order. So the first is inductor, the second is the DCR, the self-resonant frequency, the saturation current, and this is okay. Let's say that this can be either saturation, or either the current which the inductance loses the 20% of value. Okay, this can be also they can also give this. This is important. Okay, to see that I'm not inventing anything. Okay, let's find this parameter online. For instance, let's use XAR Coilcraft power. Okay. Yes, I don't care. Xar, don't know what it was, but yes, one of them randomly. I don't care. Let's open the datasheet and let's see if it was. Okay, okay. So the first was the inductance at plus minus 20%. I said the second was in DCR. Okay. The third was SFR, high saturation. Let's see on 5. DC current at 25 that causes inductance to drop of 30%. Ah, okay, okay, okay. Like I said, like I said, this could be the value of 20%, to 20, 30%, as I said before. Okay. Um, and then this is the ERMS A. Ah, so the current that causes the specific temperature rise from 25 ambient. Okay, so this is was info more or less we got it there. The current that can cause you the temperature rise, how it behave with temperature. More or less, we got the picture. Okay. That the first was inductor, the second was DCR. Okay, so we got the picture. Uh Maybe if we go forward in the datasheet, we can even find. Okay, so as you can see, these are the frequencies. And these are the inductance. These are the curve sheet power inductor oxal inductor of a current, as I said before. So nothing new. This was not so hard, okay, but they wanted you to know how much experience you have in choosing the inductors, okay. So we can go on. Now the difficult spikes. Describe the plot explaining each point. Let's take this and let's put it on paint. Oh, they even obscured the name of the graph here. So they even want you to know what is B and what is H. Okay, okay. So okay, so basically here okay, B is the flux density, guys. It's the flux density, and H is the magnetomotive force. Is the magnetizing force. Coercive force. Okay. Coercive field. Coercive. But my physics test called it coercive field, if I'm not mistaken. But anyway, let's analyze A, B, F, C, H, and all this point here. So point H. Point H is the saturation point. This is easy. Okay. This is when basically you have completed the first cycle, the field has saturated, and so this is the saturation point H. That's it. Referred to B, of course. Then you go here to B. B is called the retentivity. So here is called retentivity. You can find these names online, by the way. Okay. And they forgot to put the red box to F, but B and E are the same. Like also this is the same. This is the just negative saturation. Okay, that's nothing new under the sun. And this is just the negative coercive force. Okay. C instead is the coercitivity. The coercitivity. Now let us explain how this point here and this point here influence your behavior. So basically, in a hysteresis loop, this point here, okay, this point here tells you how much. So the key point is this: how much magnetic field is still present when the current, when the external magnetic field is zero. This is the physical meaning of this point. So it tells you how much magnetic field is present when the current I. Yes, because pay attention, you find most of the time H here, okay? But since, as I told you, since H has is proportional to N and to I, okay, you can put I here. So you can interpret this curve in a better way and say, when the external magnetic field is 0, how much residual field I have. So this tells you how much residual field I have. And if you understood this, you can imagine that I want this to be extremely high, okay, if I have to design a permanent magnet. For instance, for motors. Permanent magnet motors, do need something like that. But instead, if I want to design a flyback, my flyback converter, okay, I want it to be very small. Because since I have to make switching cycles, here I'm going to make switching cycles, I want the hysteresis cycle to be as low as possible. And I don't want to have an high B of R. Okay? Basically the same, basically you can use the same definition here. This is how much current you need to use to bring the field to 0. Okay? I use the current again. Yes, I use the current again, I know. But it is easier to understand how much current you have to use to bring the field to 0. So the higher this, and the higher the current needed, and the higher the losses. If you understood this, I think that you can immediately understand this question. So, given the parameters in the table, describe each of them and explain what family of ferrite they belong to. Soft, hard. So, for power electronics, if you understood everything, you will need the second one, and these are called. Let me bring this on Paint. So these are called soft magnetic material. Did I to pick red? Soft. Vabbè, va. Prima il verde, poi il rosso, poi il giallo. Non sta cagando più niente sto paint. Blue. So you have to use soft magnetic materials, and this is hard magnetic materials. Okay. Again, this is BH. If they didn't trust you enough, this is BH again. This is I think it was written low coercive force, something like that. You know, this parameter. Now we have to relate this parameter to this graph. Not all of them can be related because LG and LM are not present in this graph here. Not directly. If you increase LG, we increase the current capability. I will show you later. But BS, okay, let's analyze this. So BS is higher, or equals BS higher than BR. So BS is the saturation B, and BR is the residual B, or the residual. And so this value belongs to this guy, because as you can see, this is very, very large. This is very, very big, and also this H here is very large. Okay, so you want to know how can you, the next question was how can you simulate this in LTSpice? Let's open LTSpice. I just wrote them all to you here. How can you do this? You have to take an inductor just take this line, and you have to write this. So instead of writing L equals to 100 micro, for instance, you write these parameters here. Of course, you have to cancel from it. Let's cancel also this, and let's put this as a comment. Okay, first you have to stimulate the inductor with a current source. And now, since here is mainly referred to an AC input, an AC input, you basically need an AC current as well. Okay, so let's use I don't know, a sine between 0 offset, amplitude of 1 amp, frequency of the switching frequency. Let's define the switching frequency as dot param fs equal to 10 kilohertz. I choose 10 kilohertz because most of the time, if you go to a ferrite site, like a ferrite website, like ferrite, ferrite. Okay, I didn't remember ferrite. Okay, most of the ferrite here will be in tested at 10 kilohertz. But by the way, let's move on. Let's call this ind. Okay. Okay, now what we have to do? We have to extract the parameters. So how we can do it? We have to come back to the formulas and to the physics. First, we have to extract the voltage across the inductor. When a current is passing through an inductor, the voltage VL will be equal to L times di over dt. Now, since L is given by all dot parameters, we have to say, sorry. Today I'm drunk. Yes, today I'm drunk. L is equal to VL over di over ddt. I put a D match. Then, how to extract B? B, by definition, is the integral is 1 over n over a, n times a, times the integral of VL in the t. This can be done in LTSpice just by using the IDT command. Okay. And then we need also H, but H we can even omit that because it is I times N over LC times L gap, L G, L watts. Okay. Okay, so let's use first the BV. We need the inductor. We can even skip this. Because the voltage across the inductor, we already have it, so we can even skip this. Let's directly calculate B, and I think that's it. You can even stop at B. Just let us put just a load of 10 kilo or 1 kilo, something like that, not to leave open. And then let us write the equation here. So we have n, we have everything. Let us write edt of v ind over n times a. If I did not make any mistake, we should make the stop time 1 over fs. Ah, sorry, I did forgot a parenthesis. Let's run. Okay, stop time 100 micro. I did write 100 micro. Okay. But I want to... Oh my god. 1 over fs. Why? I did write it. So bugged. I want to step each cycle. Okay, so this graph has no meaning. Okay, it has no meaning. But if we did everything correctly, okay, as you can see, okay, no, there is some meaning because here you can see the saturation of the field, more or less, of this, and nothing. Just use VB and let us put here the current I of I1, and as you can see, you can know, or you can see it. You can see it. But let's do step by step. So the first cycle 0 to 25. Again, it's not working for some reason. It's not working. I don't know why. 0.25 times fs. So let us analyze step by step what is happening in the Ferrari, because I want you to understand what is happening, okay? So here there is the sine, and here there is the first. Let us use a bigger brush. Let's use a color. First, you do this, and once you do this, you reach the peak of the sine, and so you do this the first time. Then let's use the green. You do this, and then you start to go in the other part of the curve. Then you do this. You go here until you saturate. Yes, because you are basically doing the same thing as the red now. And then with the orange, we come back to here. In the next cycle, so in the blue, which is here, you will not pass in the red, but you will pass here. And then in the other cycle again, in this color here in the Heizer, you will go over the green again, and the cycle will repeat. So let's see if I told you the truth. 0.25. Now let's go to 0.5. Okay, as you can see, we are coming back. Now let's go on. 75. Now we are going down. Now 1. It didn't now 1, and we come back here. And then, okay, let's increase to 1.25 because then we start a new cycle. And as you can see, you go there. You don't take again, as I said before, the red curve. This is just the first time because here you are starting from oh, this is so big. You are starting from 0. So first you have to load it, okay? And then you repeat the cycle like this. Don't believe me? You don't believe me? Okay. Let's just repeat for 1000 cycles and you will see that I am right. So this times 1000. Okay. Whoa. Okay, maybe a little bit too much. Maybe 100 is enough. No, it's too much, too much. Okay, as you can see, I repeated the cycle 10 times, but I passed it a lot through here, a lot of times through here, but I never passed it again this point here. So this just one time and the other times in the other part of the cycle. As you would expect it to be. Now we have to make the same. Here they can also ask you, what happens if you increase the LG? Okay, you know that if you increase the LG, let me draw it like this, please. If you increase the LG, you will have a greater shift on the other side, meaning that you will have something like this. Okay? The current capability will increase as well. And to make you see this, you have just to put in the LG the parameter x. Okay. Now I'm gonna make you see. And please just put reasonable values. You will not have 1 meter of LG, 1 micrometer, 10 micrometer, yes, but 1 millimeter is very big, okay? So let's put dot step param x, dot step param x, list, first value 0.00001, and the other the same with but without the 0. Okay, so let's run the simulation. Not for 10 cycles, because otherwise it becomes impossible to read. Just one cycle is enough. And let's run the simulation. Oh! Are you seeing this? Guys, this is so beautiful! Let's put 5 amps. Oh, now you can see. As you can see, I increase. So the first is the with the lower LG, and the second is with the gap increased. As you can see, as I increase the gap, more current can flow into inductor. For this reason, I said, let's put the current on the x side, on the x-axis, because you can understand directly the meaning of this graph, okay? With h, I can put h if you want, but you won't understand nothing, in my opinion. So here, what does it mean, minus 60 volts, minus 80 volts? You don't have any meaning, okay? It doesn't have any meaning, okay? Let us see if we put another one and how much we increase. Okay. Let's see. Oh, I see that if you do that, you will go to how much amps? Wow. So to even to 20 amps even. Wow. That's interesting. That's interesting. That's very interesting. So this is very, very interesting, guys. Very, very interesting. I'm sorry, what he was asking us? Ah, yes, he wanted us to also to put he wanted us to put Let's use maybe like just lower values because perché non li piglia? Deve essere così coglione. Just a small. Okay, so I'm just so beside a value, you will not basically you will not have anything. Okay. Now let's see if we can even plot if we can do the same. Let's see if we can do the same with the other one. I would like to superimpose them, but I have to make a number 2 on them. So for now, let's do something like that, okay? Let's do something more interesting. Let's save this plot. Yes, let's do this. Let's save this plot here on Paint. Let's save this plot here. Okay. And now, let's comment this. And let's put the directive in here. .param here. Okay. Let's run. Oh, so as you can see this time, as you can see, this time we have a greater, a higher saturation. So this is probably indicated for so this is probably an inductor for hard but it is strange because it has a low H of G. It has a high value of saturation but a low value of coercive force. But I didn't choose the parameters, so maybe there was a mistake on this side here, or I don't know. But anyway, they wanted us to understand. The concept here is, aside from the values, the concept here is: can you understand this curve here? Can you simulate it? How can you simulate it? Okay, and if you can have a deep understanding of magnetism and etc. So this is, aside from the values, which maybe can be even wrong. This is the real meaning of the interview. Okay. It has been a quite long video, and I don't have time to do even the second part. Okay, the device part. So I think that I will close the video here and see you in the next one.